operation of information aggregation. Second.
Okay, let me get organized. It's to make sure that my coffee stays with me and at the same time doesn't end up on a computer. I guess like the rest of you, I'll start out with a chart or some thoughts that actually date back to the early 70s about where experimentation started. And since I assume there's many people out here who have no idea what experimental economics and related things are about, it'll serve as a little orientation. But let me tell you where we're going. I'll just start by giving you a little background, and then I'm going to move to a problem in design. And of course, this design is guided in some sense by game theory. The problem is the following that I'm focusing on. Nature's done something. Each of you receives a little bit of information about what nature did, just a little, okay? You're not in a room together. You cannot tell me what you observed. What you observed is held as intuition, perhaps as a subjective probability, perhaps as confusion, perhaps as a muddled strategy, right? In any case, it's subjective. If I ask you to fill out a memo telling me what the probabilities are, you'd write back and say, these administrators, I hate them. They're always asking stupid questions. I have no idea what the likelihoods are because I don't even understand likelihood, right? The question is, can I present you with a very natural way and incentivize you? In this case, it's going to be a type of betting, not really betting, in a way that you guys can express yourself. The system will collect what you believe. It'll aggregate it like a statistician, like Bayes' rule. And by me watching the system behavior, I can deduce what I would have known had I observed directly what each of you observed, right? So that's the question. Can the system go out and, like a vacuum cleaner, collect the stuff, apply Bayes' rule, and then publish it for us all to know? Now, actually, in economics, we have models like that. They're called rational expectations. And in markets, they work something like this. And this is a fact, by the way, experimental fact. What happens is, if it's a good year, nature has told some of you, hey, it's a great year, giving you a strong signal. Some of you have a weak signal that it's a good year. Some of you have a weak signal that it's a bad year. Some of you have a strong signal that it's a bad year. But if it's a good year, because of the laws of probability, a few more of you have the good signal or the bad signal. When you then show up at the marketplace, you know a couple things. If you say it's a good year, you know that your signal is really strong, and you know you're not alone because there's other people out there that might have received a signal. So given your strong signal, what you'd really like to do is get in there quickly and take care of these dum-dums and steal their stuff at cheap prices. So you put in a very low bid, cheap talk, right? And it's sitting there in the book, and you're saying, wait, I hope one of these dum-dums show up and take it because I'm going to steal it. On the other side, somebody who believes it's a low state has put in an ask very high, right? Well, I know it's good, and now I know that these other people out there have good signals, and one of them, say Linda, sees me being exposed to the dum-dums, she also having a good signal, puts in a bid just above mine. What do? I say, damn, right? And somebody else has a good signal, might put a bid right above her. Now, on the ask, there's not very much competition because not very many people know or have the signal that it's a bad year. So the competition on the bid side is fast. The competition on the ask side is a little slower. It'll take the market about 30 seconds to know what the system is. And not only it's not mimicking, by the way, Jerome, they actually seem to be inverting what the other person knows, saying if they're doing this, then they must believe that, putting it together from various and sundry points, and then jumping to the equilibrium. All right? Now, I fish, by the way. Often I'm not quite out here, but often I'm out on the ocean catching nothing. How do I determine where the fish are? How? By the birds. By the birds. We have a fisherman in here. I don't see any other fishermen. I don't have sonar. I don't have radar. I watch the birds. Now let's think about that. A bird has a brain maybe about that size, right? This bird is watching another bird because it has a lot better eyes than I do. And if you're out on the ocean, these birds stack up. They call them stacks because they're competing to get to the sardines that are down below them. Now, the sardines have an even smaller brain, but they know the big fish are down there below them, and so they're coming up. So now think how complex this is. I'm depending on the rationality of something that has essentially no brains, using the system behavior to go back and know something that I cannot know and no one told me. It's communication without communication. All right? If you're at a strange place and you want a restaurant, how do you figure out where to go? The crowd. Same thing, right? So we do this all the time, right? So the idea that it could take place is not just dreaming. It's around you. You do it. The idea is, can we make that systematic using principles that we think will work and then apply it to something real? So that's the problem. Now, it starts out actually with an experimental economics, and I'll show you an old chart. We called it the fundamental equation many years ago because I was trying to understand what it meant to do an experiment with a political economic system, right? The whole thing. And what is it I'm theorizing about? Well, we have preferences. Almost all the models, game theory, coming from Luce Rafa and other places, say that basically the preferences we're going to take as parameters. Okay? We have institutions and information. Now you can see the structure of an extensive form coming out of this already. We have feasibility. Of course, a game theorist would call it consequences. An economist would call it the commodity space. Right? A political scientist would call it the candidates or the options. And then we have the outcomes. All right? Now this not only is the structure of a very general kind of philosophy of games, it's also the structure coming out of axiomatic social choice theory, where the object in axiomatic social choice theory here, well, it's just a mapping, might be preferences. I'll talk about that in a minute. Now, what was that? Okay, now what do we have? From a behavioralist point of view, well, we have principles of individual choice and behavior, and then we have these solution concepts. Now, if it's a competitive process, you might say the solution concepts is the competitive equilibrium. Could be a Cournot equilibria. It could be Nash equilibria. It could be the core. It could be a family of von Neumann Morgenstern solutions. But we have this concept of a solution concept, which itself is determined by this stuff. And so the question is, if I can control this stuff, then I can test that stuff. Or if I believe this stuff and see that, I might go back and be able to infer what that was. So this equation allows you to go back and forth if you could control certain kinds of things depending on what you could observe. So in revealed preference theory, we'd say I observe the outcomes, I know something about their information, I'm going to deduce their preferences. If it was revealed institutions, I know their preferences, I know the outcomes, but I don't know the rules of the game. Can I observe the system and go back and figure out what those rules were? So we can go back and forth across this in a very broad way. The only trick is, look, we have to control these things. And being an economist, it's very easy. We use incentives, and in this case we use money. Typically it's an abstract outcome space. As long as somebody prefers more money to less money, I can use the idea to induce an ordering over an abstract space. So if I want you to choose over the letters of the alphabet, I can say, hey, if you choose A, I'm going to give you $50. If the group chooses B, I give you $2. If it chooses C, you pay me $1. If it chooses D, 25. As long as you prefer more money to less, I've induced your preferences over that set, and I can do that for every individual in the room, and I can give them different preferences. So I can create any conflict I wish. I don't let them, and I can control their communication and all that. And so that's going to be the way we're going to start this. Institution, well, those are just the rules. I'm an experimental, follow the rules. I hope you can understand them. Okay, now what's happened recently? It's kind of where we're going to go. Well, we have a whole series of new theories, much of it generalized by game theory, coming out of public choice, mechanism design, rational expectations, information theory. We're just seeing an enormous amount of mathematical theory being generated. We also have new technologies. Now I can actually create almost any kind of institution you can imagine, computerize it, and have the participants located all over the world in real time. All right? So we have this capacity now to create very, very powerful kinds of mechanisms that could never exist before because of the speed of communication, of writing things down, of verification. All of that is just really instantaneous these days. So we have the new technologies. That means the new theory is implying something about institutions that might solve a problem, purely theoretical, purely on the pages of some mathematical economics or mathematical social science journal. The technology actually allows us to create those institutions suggested by theory. The behavior, well, we can induce preferences, induce some control, and actually use laboratory techniques to study it. Now we're going to be able to, I'm really talking about design at this point, not only the science. We could talk about just pure scientific. With new laboratory techniques, I'm going to ask two types of questions. One is, from this theory and the implementation, will the system behave as I want it to, or as I think it should? That's one question. And I can run the experiment and find out whether it does or not. Do we get to a Pareto optimum? Is the distribution I generate appropriate? Do we achieve a competitive equilibrium, if that's what we're after? So that's called proof of concept. But there's a different thing I have to worry about. I'm going to call design consistency. If I'm going to have confidence in this design, it has to give me the right outcome for the right reason. In other words, is the design consistent with the principles, the behavior in the design consistent with the principles that I used to design it in the first place? So it's not just going out and saying, hey, does it work? No, it's got to work for the right reasons. You need to know that before then you can go out to implement it in a very complex thing where the environment's nothing that you have control over. So it really has to be robust. The robustness comes from the theory. The theory, by the way, we can thank Lucian and Rafa for much of it, because all of us, you can see, buried even in this philosophy is this structure. Okay, so now here's the problem we'll worry about. Something happens. Okay, individuals receive some kind of signal. Of course, we want to know what was it that happened, but everyone has a different opinion. We then create a system where these guys do something. They buy something, they sell something, they place a bet. That's up for us to decide what it is, because we could design what it is, right? Then we want to watch what happens and see if we can predict what happens. So if I'm watching this, can I then go back and decide what that was, or at least what the probability distribution over that was by watching the behavior alone? That's what I'm going to claim is possible. That's what I'm going to claim we see experimentally, and I'm going to show you how that's used in the field, in actual reality, in several different contexts. Okay, from an experimentalist point of view, here's what happens. Here's an urn. Nature chooses something. in this case C, randomly. So there's 6 things here. This is a uniform distribution, so each one of them has a 1/6 probability. One is randomly chosen. Now I'm going to create another urn where this chosen thing is a little over twice as likely as anything else. Okay? So now I'm going to draw from this urn. I'm going to give you 3 observations with replacement. So this guy gets the observation CAA, this guy gets ABB, this guy gets BCE, etc. Now notice that there's lots of different opinions here. Let me move this, by the way. I see Brian about to break his neck here. Okay. So let's take this guy. He thinks it's A. Of course, he's wrong. He's got a strong signal that's A. Here's a guy who has a strong signal that's C. Here's a guy who has a little intuition at C, but he also has equal intuition. Here's a guy, again, has no clue, BAF, right? It's just a different thing. But if you look at the collection, here's a C here, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 C's, all right? If you pool these data, Bayes' law is going to say it's C, right? Much more likely than anything else. I can also use Bayes' law by pooling these data and find the posterior odds of A, given the information that's out there, posterior odds of B, et cetera, et cetera. So if I pool the data, since I know everything everyone sees, I can then say, if we pooled it, what's the likelihood it's A? What's the likelihood it's B? What's the likelihood it's C? I actually have that probability distribution. Now the question I'm asking is, by observing the behavior of the system, can I extract that probability distribution? So I want to know more than what the state is. I want to know the probability over the states given the information that's out there to get. If I can reproduce that probability distribution, I'll consider it a great success. Okay, you understand? So nature's done something. There's a posterior odds if you knew all the information that's out there. That posterior odds, if we collect it, gives us some probability distribution. I want to create a process where I know what that probability distribution is, even though I observed nothing directly, only the behavior of people. Okay, so there's no need to go into it. Okay, here's the process we're going to use. We're going to use a type of parimutuel system. It's not exactly a parimutuel system the way you do it at the racetrack. We've studied those as well. In this system, you're going to have a bundle of funny money. Actually, in some cases, you have some funny money and you have to use your own money. The system's going to open up, and there's going to be 2 things we'll study. One is a system where there's 2 stages, and another one where there's just 1 stage. So let's look at the 1-stage process first. The process opens up. There's 6 objects, A, B, C, D, E, F, G, right? You then can go and take your money and buy a ticket on A, right? And you can also buy some tickets on B. These tickets are at fixed prices, all right? The money you spent is going to be put into a pot, and then when the winner is actually announced, all those people who have tickets on the winning state divide all the money that's spent on all tickets. So if he goes to the winner and buys a ticket on A, right, and if he's the only thing that's purchased, and it turns out to be C, he loses his $1. Okay? Suppose it turns out to be A, he gets his $1 back. Suppose he puts on $1 A and somebody else puts on $1 on B. It turns out to A, he gets the $2. So if he bet half the tickets on A, he's going to get half the money spent on all of them. The thing we're going to be watching is the proportion of tickets purchased for each of the items. We're going to normalize that and call that a probability distribution. So if I see 100 tickets purchased, I see 10 are on A, 10 are on B, and the rest are on C, right? So I would say the probability is 1 in 10 is A, 1 in 10 is B, and 80 out of 100, 8 out of 10 that it's the other one, right? So that's the thing we're going to be watching. So, nature makes a decision and sends out signals to all the individuals. Okay, so you go to the betting window open, and the odds develop. These are just, and by the way, these odds are in real time. So anytime it goes to any window and purchases something, everyone knows it. So there's a real-time tracking of everything everyone did. That means that if you think it's A and all of a sudden you see that everybody is buying C, you can say, wait a minute, maybe I ought to jump on the cascade. It could be C. Or maybe I need to rethink my probabilities. That means in this system you're going to be learning from the behavior of others. It's like watching the fishermen, right? So if I see a bunch of fishermen and I'm going where they are and I see someone leave, I'd say, maybe not, right? So the odds are going to develop. Final odds are noted. Okay, so if I pooled all the information, I'll get a distribution like this. Right, that's just the posterior odds, given I've pooled everybody's information. I'm going to call that the aggregate information available. That's all there is to know. There's nothing more. But then I'll look at the normalized odds, namely the percentage of sick and told. I'll get a different distribution. Now the problem I'm going to have is this distribution in some sense close to that distribution, right? Well, as it turns out, we're going to use several different measures, Kublik-Leibler we're going to use, but the one we're going to find most useful is the difference between the two, right? Actually divided by 2. So our measure in this function space is going to be a very simple measurement that we're going to.
So I normalize odds, people place bets, and you just accumulate those. It's just.
Yeah, and you can't go back.
It's a histogram. Yeah.
This is a histogram, literally a histogram. Now this histogram is coming out. I'll show you all the time in real time, but so it's a very simple process. Now we know, by the way, that in these processes, what I just told you, that there's going to be bubbles. People are going to think, oh, it's A, and they run out there and buy A, and you're going to see these, what we'll call them, bubbles. And he's going to say that A is just 100% or 90%, and it is not. And the aggregate probability available is going to say it's not even close, right? Those things are going to happen. The thing we're going to discover is that when they happen, it almost always happen when the information is bad. So if the information out there to get aggregated is not good, it's more likely that there's a bubble, right? Which kind of makes sense. So we added a game which basically says is going to give you a feeling whether there's good information out there to get or not. It's going to be a pre-stage parimutuel where you don't get to see anyone's betting. You have funny money, so you need to spend it all, so there's no risk aversion. You place your bets any way you want to in the absence of anyone else. Then we reveal that, and then the serious game starts. But if this thing is very flat, you know immediately that the information is not very good out there. If it's very peaked, you know basically that's a bunch of modes, but a bunch of modes may not be the best thing to do, right? So, so we're going to call that a 2-stage. Now, also to cut to the chase, is you guys can think immediately, since there's a room full of people guilty of game theory, you know immediately the strategy to do is wait till the end. Don't buy anything because you give away information. Well, that happens. We saw it happening. So we said to ourselves, being economists, how can we prevent that? Well, remember I told you that the price of the ticket is constant, or just given to it? It's given to you, but it's not a constant. The price of the ticket is going to go up very rapidly after a given amount of time. So if you wait, sure, you can withhold your information, but you're going to be able to buy fewer tickets. So now this is an incentive for people to get in reasonably early, right? So notice what we've done. We've First is we've given you incentive to buy according to your subjective beliefs. Secondly, we've given you an incentive to reveal whether the information in the system is good or not, to be aggregated. And third, we've given you incentive, you better get in there and do what you can early so that all the information doesn't come in after the bell, right? So we can really get aggregation. So these, by the way, these are very natural things that game theorists would think about. Of course, we saw them happening. We didn't think that they would happen. We thought maybe not. Well, we had to change the system. So the system you're going to be watching.
Did you play with that at all to see how much people value withholding information by changing what the incentive?
We could. We haven't done that. They will. If I showed you one that, for example, is the same thing, only now there's a period. We'll say a bell will land, and it's going to end randomly sometime within the next minute after that bell rings. Essentially, nothing happens until the threat comes, and then boom, all of them come in, and you'll see it. You'll see the time series looks like this, just right there, just after that bell. And of course, there's no information out there. If the fact that you've got a losing opinion doesn't come out for you to know till it's too late. So it doesn't aggregate. And if you do that, you're going to get many more of these bubbles. So we're trying to get rid of the bubbles, right? And it's a design problem, right? So we're free to do anything that we think will work.
This is illegal gambling over the internet.
Actually, no.
Oh.
No. Depends on which part of it is. The ones that you're going to see, were all done with a funny money where there's a prize. I should say that. Now, to get away from this problem, what we did then was say, okay, we've got problem taking money from people. What we're going to do is put up a prize of several $1,000s, and you're going to be able, and we're going to give you, say, $500 of funny money. You can, of course, you want to spend it all because it's worthless, and you can use it to buy the tickets as you would your ordinary dollars. So now you're actually competing for a large prize, and with funny money. So notice the incentives are essentially the same. We've taken risk aversion all the way out of it, and so it looks like it should be. So and we're not gambling. Yeah, that's very good. I'm sorry that you mentioned that, because we do it both ways inside our subject pool at Caltech.
Can't you get Congress to approve an exception for your?
Actually, there's a memo circulating, and I'm not in favor of that memo right now because it says markets, and the things we're doing are not markets. We're doing other things. So I'm afraid if Congress approves the use of markets for this kind of thing, they're going to look at this and say, hey, this is gambling. So I think there's externalities involved, but there is a paper circulating. What's that?
They're going to exempt the Iowa.
It was a letter of exemption, a letter by the Futures Commodity Future Committee said we're not going to look at it. It didn't say you could do it. It said we're not going to look at it. Okay. So and we've been doing this for a long time. We're an educational institution, and but as you get into businesses where I'll show you some stuff from Intel, I've done it inside several businesses, they worry about it. And
Hedging funds. Hedging funds.
Hedging funds. Well,
This
this is
is
a kind of hedging
they have
fund.
a faster computer by the microsecond than you by seconds.
Yeah.
And you get in at the beginning of the shaft.
The hedging fund is okay, but they've also got clearance from they're regulated. So, okay, so let me go on. So you guys understand then what we're seeing, and so this would be the normalized odds. This would be a good estimate. So this is the odds that we actually see. That's the truth, the best we could do. That's really a good outcome there. A cascade or a bubble would be something like this. This is the aggregate information available, the best probabilities if I aggregate it, but the system tells me it looks like that. So a distribution like this would be what I'd call a bubble, or there's other names we can call it. So, and I'm going to talk about weak and strong bubbles. This is going to be, so that's a good outcome. This is the truth. A weak bubble is one that looks something like this, it's just a little, its peak is just a little higher than that. A strong bubble is one where the mode is over twice as high as that. So it's really giving you a strong signal that it's here when it's really over here. So, and the thing we're going to discover is as we do these things, these strong bubbles essentially are going to go away. We're still going to have some weak bubbles from time to time. Okay, here is, by the way, this is with one of our graduate students, Kevin Rouse. Here's an example. This is spending over time. This is the total amount that could be spent. You can see it starts out. This is, I think this is seconds, 12 seconds. These guys are already up there, kind of levels out. If I look at the probability distributions, there's A, B, C, D. You can see that what I retrieved is almost identical to what there was out to get retrieved. This is not unusual, where it's just perfect, right? Here's another one. You can see the amount of spending on each of the tickets or each of the horses. You can see it's kind of spread out here a little bit more. This one pops out. It seems to be it, right? That's B. You can see here B is the actual one, but it's telling you that the probability of B is much higher than it actually is. This is the truth here. I don't know, posterior odds is what they meant. So this is the posterior odds. So the system is saying B is a lot more likely. So that's a little mirage there. You can see it's telling you that these out here are not likely at all, when in fact they are. So here's a serious mirage. You can see it actually gets in there really fast. Okay, very fast. It really is telling you it is D, right? No, it is D. If you knew what it was, the system's telling you it's F. Just basically don't look at anything else, and with a little bitty probability on D. Now in this one we were interested in one more thing. We said, what happens if we repeated this so the information's the same, but no one knows what the outcome was? So everyone knows that it's exactly the same distribution of income of information. It's exactly the same. People know what. It is the same outcome. Of course, you don't know what that is. You saw the previous one. You learned what there was from it. We know, because we're looking at this, that what you learned was wrong. Now the question is, if you do it again, does it get corrected? And the answer is no. Now you get a really violent bubble. Not only do they do what they did last time, but they get there almost instantaneously. So now they just force themselves into this bubble that we know exists. So going through the bubble itself and repeating it is not something that's going to clean this up. It's going to reinforce what you saw previously. Okay, does it really work, and why does it work? Okay, now I can tell you something we know about this. These are just looking at these distances. If we do the two-stage, this distance, this intersection distance. Remember what I was saying. There's one distribution. There's another distribution. So basically, I'm looking at half of this, right? So if there's a great deal of overlap, this distance measure is very small. So on the two-stage game, this is on average across many of these. This is the error term. If I asked whether people if I put a model in place of decisions and said, take your information, assume that you just dump it in a decision theoretic way on the most likely, and we aggregated those odds, what would we get? Well, that would be our error. So that decision theory is not nearly so accurate as what's happening here. Right? That's telling you that information is actually becoming aggregated, that the system is knowing more than the modes of the individuals. In other words, as you watch these other people, You in somehow or another are getting information, you're updating that correctly, and as a result, the system acts better. So there's some kind of synergy going on here among the information. In other words, it is becoming aggregate. What we're getting as an outcome is more than decision theory would say that you could have. All right? If we just do it one stage, we can see our inaccuracy goes up. If we took the average of beliefs, many times people will say, oh, I know what they're going to do. They're just going to take the average of everyone's beliefs, and that's the way it's going to turn out. No, that's a very bad model. So if we took the average of beliefs, this would be the level of error. If we said that they ignored anything learning in the system, they just went with their priors, this would be the level of error. So we're actually seeing the level of error go up or down as we move towards the designed system. Now we can go on with that, and I'm going to show you a few more things. This is just another. Here's a series of behavioral models in comparison with what happened. I think this is useful. Again, we're measuring this distance. This is what we call the Wirtz distance. If we take how close is the one-stage model, just the data coming out of a one-stage parimutuel, how close is that to the truth? That's that number. Okay? If we come across here, we see the one that's closest to the truth is the pure decision theoretic model. This is equally likely. This is average beliefs. This is pure rational expectations. So if we just have the one-stage model, they just go out and do it, we'll find out the decision theory model actually does quite well. In fact, it does better than rational expectations. Okay? Let's suppose we repeat the round. So this is now it's two stages, but we're just repeating. Once we get into the repeating, on average, the best model is the pure rational expectations model. It's better than the decision theoretic model. Okay? If we look at where we have a two-stage model, and just look at the first of the two stages, average belief comes out. By the way, average belief is very close to a type of competitive equilibrium. All right? But then if we look at the whole system, again, rational expectations is by far the best. So we're seeing this kind of magic come out of the model that we see and we discovered in the late 70s about rational expectations. In markets in the late 70s, we discovered that, as a matter of fact, markets themselves can aggregate this information very well, and so rational expectations work. Now we're beginning to see how broadly is that intuition and body of principles work, and we're saying it's quite broad. Decision theory model says you've got your signal. You just turn right around, and there's two ways we could do it. You could invest it proportional to the probabilities, or you can dump it on the most likely. This model says you're dumping it most likely. You're not going to get a lot of difference between those.
Strategizing, choosing the optimal time.
You mean in continuous time? Yeah, this is though you're not paying any attention to what anyone else does. You just got your private signal, and as you would in the competitive model, without any rational expectations. You get your private information, you send in your demand function, given your private information. This says that that's wrong. That's not the way it works. That it's going to be, you've got to add rational expectations to it. Okay. Now, this is a little bit different. This is going to say, I'm going to look at the best information, and I'm going to say, well, what's the given the truth, given the aggregate information available, what's the size of the mode? So I would say the information is really strong if that mode is really high, because all the information, the posterior odds says one of them's 80%. Okay? If that mode's very low, then I would say it's kind of flat. So the information to get is not so good. The variance must be higher. So the entropy a little higher. Okay? So then the question is, what's the likelihood of one of these mirages as the quality of the information decreases? You can see the likelihood of a mirage is actually is increasing as the quality of the information decreases. Okay, so now remember, I'm measuring how close we are to the truth, right? It's telling me I'm getting further and further away from being able to detect the truth. The worse and worse are the more difficult or less, more variance is in the information to get, right? So it's going to be harder for me to get information that's kind of dispersed. It's going to be a lot easier for me to get information that's quite peaked, all right? And that's going to be a phenomena. Okay. Now, one thing seems to be quite clear. These guys are learning something, seem to be learning something from what other people are doing. Now, where is that coming from? Are they? And where is it coming from? Here's the first thing. When they're submitting their own money, they buy fewer tickets when there's a mirage. Isn't that interesting? So if there's a mirage out there and no one knows there's a mirage, it's detected in guys being less aggressively buying. In some sense, they're sensing something they cannot know, right? Something's a little wrong, right? So they hold back. So if you're watching the system and you watch the speed and the amount of money that's coming in, the less aggressive they are, the more likely it is you're getting a bad signal, that the system is telling you something that's wrong. So it's kind of, system is doing its own diagnostics. It's saying, you can trust me this time, but if they're not spending much, maybe you shouldn't trust me so much, right? Which is kind of phenomenal, right? Quite phenomenal. Where's that coming from? What's that?
I mean, that is indeed what you do at the horse races. You wait and see at the very last minute what
the structure looks like.
owners that know about.
Yeah, well, let me show you how that's working.
Yeah, but I might interject. I mean, it's exactly the reverse in the stock market, isn't it? It's when you get these bubbles, people are coming in more rapidly.
No, actually, in the stock market, I can tell you what. Let's talk about stock market in a minute. Okay, it's related to what we're seeing here, though, so it's not off the subject. What's happening? The speed of tickets sales is slower when the information's bad. So not only are they spending less, they're spending it slower. And here's the amazing one. If we look at the entropy of the system, and this is probably where the information is coming from, when the information is bad, you see this floating around to the odds. So if you're watching the posterior odds or just watching the distribution, when the information is bad, you're seeing this kind of wobbling. It stops and it takes form, but when it starts out, if you see it wobbling, that means the guy who's throwing it doesn't have a very steady hand. The information you're getting is really not that good. Be careful, all right? So we think that people are actually detecting this from the entropy of the system, and they're going to see it very quickly, all right? Now, with respect to the stock market, you can see very, very similar things, but it's always in the bids and asks within about the first minute. So it's really fast. Okay, now I'm going to close with some actual examples of use. All right. The first one I'll show you is Consumer Price Index forecast. This is what the screen looks like. The participants are members of the National Association of Business Economists. There's going to be about 20 or 30 or 40 of them through a whole series of these predicting what's going to be the Consumer Price Index announced, I think, a week from now, right? And here's what they're doing. Is it going to be down 2%, up 2 points? So here's the percentage changes. Okay, you can see there's lots of horses running. This is the amount that I buy. This is the proportion that this ticket has received by everyone. So the moment I buy something, mine goes up, the proportions go up. As anyone buys anywhere, this chart's changing. So it's just changing all the time, right? Up here we have where is it? Here's the total amount of tickets sold. Here's the price per ticket, which after a few minutes is going to start going up fairly rapidly. And this is, I think that's the amount of time left, maybe. I'm not too sure what that is. Okay? So this is what it actually looks like for these guys. And they're logged in. We know who they are. All these guys are professional forecasters. They're all professional econometricians who watch these numbers.
But they're ignorant of the theory.
So I don't know what they know about the theory.
Well, I mean,
I don't know. They're econometricians. They're supposed to be Bayesians, you know. No, these are all professional forecasts. These are all guys, econometricians who deal with macroeconomics. They're supposed to be pros. Well, let's find out. Okay. Well, the other thing I'm going to do is with a bunch of people who are actors and directors and producers of films in Australia. And the question is, what's going to be the box office of a film that's going to open up in a week or two for the opening weekend, and then what's going to be its lifetime over the lifetime that the film is circulating. And these are people, presumably in both cases, these are people who have good intuition and knowledge about this phenomena. Okay, here's the, well, I thought I was going to give you a one from the professional forecasters. They all look very similar. This one, by the way, is F911. This is the probability distribution over the tickets. That's the cumulative. That's the medium. And this was the actual. You can see we got way low of what it was going to be in this particular one. At least the median was. This one is, what is this? Oh, Spider-Man, yeah, okay. So here's the actual distribution of tickets, okay? See, it's multiple moded, which shouldn't happen. That was our most likely. You can see that that's what actually happened. So we overguessed here, right? Now, let me make a comment about both F911 and Spider-Man. Both of those distributions, if you looked at prior, had never sold this levels at all. So we're already out of the range of previous histories, even though we're guessing wrong. Which one is this? Shrek 2? Same thing. Okay. Now this is an interesting figure. Now it's going to, if I aggregate all these, how can I determine how accurate I've been? Now if you think about that, there's a clever way we can go about that. If my probabilities are correct, say I say it's 25%, then every time, if I collect the times that I say it's 25%, I should be, or less, I should be right 25% of the time, right? So if I say it's, it's going to be at least this 75%, every time I say that, I should be right about 75% of the time if the probabilities I'm using are the same as the probabilities. Now that means that if I go back and look at the relative frequency I'm correct, given that I've guessed 10%, given I've guessed 20%, the relative frequency should be uniformly distributed. Go back and think about it if that's true. Okay? So now I can use the uniform distribution over the frequencies to determine my accuracy across all these things. And here they are. This is the probability predicted. That's the uniform distribution. Of course, since it's constant, it just should go up at a constant rate. And that's the actual predictions accuracy. This is statistically indistinguishable from that. Now, we've done this lots of times now. We've done this with economists. We've done this with film directors. As well as I could tell, it's turned out really very, very accurate. Oh, this is the July farm, non-farm predictions. The business economists were proud to compare their predictions with Bloomberg. This is the predicted cumulative. The actual is here. The mode of their prediction is here, and Bloomberg is way over here. So typically they've been doing better than Bloomberg, which they think is really good. Here's something that's happening now inside Intel. These are the forecasting group inside Intel. They want to know what are going to be the orders of a particular thing next quarter. They have an official forecast that's the dots. And then this is the distribution of these people in marketing and management participating in one of these things. You're looking at the distribution here, and that's the mode of the distribution, or the meaning of the distribution. You can see basically this thing right here is a pretty good forecaster of what the official forecast is going to be next time. So we're getting individual, and by the way, Intel is absolutely delighted with this, because what it's doing is pulling their forecasting down faster than they had it previously. So I guess that what I can say is, so this information aggregation mechanism, it's designed, it's testing using experiments. The applications are possible, but I think it's fair to say, without the intuition and formalism of game theory, and in particular lucid Rafa, by the way, because like everyone else here, that's where I started learning my game theory, this just wouldn't have happened. So the philosophy, the intuition, to the extent there's formalism, it all goes back to the same source. And now I've got to say, Duncan and Howard, thank you. It's really created what I think is a brand new methodology in terms of experimentation, a methodology in terms of testing mechanisms and design, and a new set of tools for management to use. Thanks.
And we have time for questions.
Well, let me come back to the stock market.
Okay.
Because of the, in some sense, you're testing rational expectations,
Sure,
or not in some sense, you are testing rational expectations.
Not in some sense, exactly.
Exactly, right.
Just not in a market context.
Not in a market context. And there is this debate about whether the rational expectations hypothesis actually characterizes the stock market, at least when you have these sort of end of the 1990s kind of boom, where you seem to have expectations much higher than are rational. Now, I guess your story would be then that the market is sending poor signals if you're going to get this distribution way to the right of where it should have been in terms of predicting the prices, that there are periods of time, if we do have bubbles, where the signals somehow spread out and you don't get the rational expectation outcome. Is that the way to interpret your?
Well, you're asking me about something I wouldn't touch with a 10-foot pole, because to me the U.S. stock market is just this enormously complex thing. I don't know what goes on there. I don't have any control over it to start out with. But the question is rational expectations correct? If that's the question you're asking, to test it, I think there's no doubt. Rational expectations is incorrect. Game theory is incorrect. Nash equilibrium is incorrect. As far as I know, every known theory that we have is incorrect. It's the wrong question. The question is, what's more accurate? What do we have that's better? And then if you start putting a priorities of models out there, you're going to discover that the rational expectation, by the way, beats Nash. Why? Well, because Nash doesn't take into account this kind of information aggregation, at least in the models we have now. So, now, with respect to markets and now you might be able to. I see people over on my left just anxious to get me corrected, and that's great if we can get corrected. But in terms of markets, typically if there's a bubble, now I can say something I know a lot about, and that's experiments. When there's a bubble, and they can occur, the way that there's been an odd thing. First is, bubbles will typically occur when the information is not good, just like here. In fact, that's where we started learning it, is studying markets. The second thing is, because the information is getting in so fast, in markets there's the process. Remember old Marshall's concept of how entry occurs? The guy that has the most highest value thing profitability gets in first, Marshallian dynamic. That's what seems to be happening here. The guys who have the strong preferences, the strong signals, get in quickly, really fast. Occasionally, the wrong guy gets in early. People who basically don't know anything, they make a mistake, they did something, they're aggressive very early, the information's bad anyway, boom, off you go into a bubble. Now, sometimes the market will detect it, sometimes it won't. So I don't know whether that's, responsive to, the U.S. stock market, that's so complex, and information's coming from everywhere. As far as I'm concerned, I don't know that there's ever been a bubble in the stock market. I know it goes up and down. I know I lost a lot of money last week. But whether there's a bubble in the sense I'm talking about here, I don't know, because I don't know the distribution of information that's out there in fact. Yeah.
Do you do any exit interviews with your subjects to find out the kind of reasons why they acted like that?
Yeah, we do occasionally, and this kind of thing, most of the time when I ask the subject, he doesn't know enough to answer, right? The subjects I deal with aren't trained the way you are. They don't have the language. They don't have the facility to talk. Usually if you ask a subject, you say, oh, I was trying to do as well as I can, or those guys are idiots, or, you'll get some kind of answer like that. So if I knew how to ask the question, I would. And we have done experiments where you can take a side bet on certain kinds of events, and that'll give us information that a questionnaire might. There's other places we've had quite good luck with questionnaire.
So have you done similar experiments with your Caltech student subjects?
Yeah, it doesn't seem to make much difference. A lot of these are Caltech students. Some were Chicago, some were PCC. These people, some were Stanford. These people are the subjects. The student subjects are quite a variety. I could comment on that though. I don't see any difference between the student subjects and the businessmen and the Australian film industry except one place. The students will understand the instructions. Businessmen in the film industry, it's a real hard job, right? Because they're not familiar with the institution. They don't know how to do this. They don't have a facility. The incentives are not as great. So I would say that when I see it in a lab, I tend to believe it, with the exception of dealing with people who might not understand what is going on. And that's what you get when you get business. So it's not the behavior, it's the understanding that I see is quite different. Yeah.
I didn't understand. Nash equivalent doesn't take account.
Yeah, here? Yeah, if you just have the Nash based upon private information, you get the wrong inputs.
Yeah.
But I was telling you, Nash based on private information. I don't know exactly how to expand Nash for this kind of information aggregation. Now, it could be, we have a lot of clever people here. If you can show me how to do that, it'd be most welcome. It's most needed.
It will be hellishly different.
Yeah. Because these are real-time things, and they don't know much.
Actually, there are related kind of models like Captain Leahy and so on. The paper on wisdom after the fact.
I don't know. You have to tell me about it later, because I don't know.
There's a paper by Rusticini and
Oh yeah, I've seen this too. But again, hey guys, the next step in terms of theory is this giant cliff, as far as I'm concerned. These are really hard problems. And so I've been waiting for somebody like Rob Wilson, Roger, or Ben Moore to just say, hey Charlie, you're so stupid, you should just do it this way and give me the formula that I can just walk right out there and design a new experiment and know how to process the data. So,
I
yeah.
have a rational expectations model for bid and ask.
What's that? Yeah, you do. But that's the seal bit then. The continuous? You don't have continuous.
Anyway, that's something.
Well, we need to talk about it. How to get it out is great. Oh yeah, there are rational expectations models, by the way. There's no doubt about that. Dynamics, generally the dynamics in a rational expectation are pain in the butt, But there's learning and you're updating content. There are models like that. Most of them are kind of smoothing models. But yeah, that's true. It could be that we just haven't looked on it. Yeah.
Charlie, just sort of two interrelated questions. There's two old literatures. One, of course, is the Keynesian Beauty Contest, and my amendment to the Keynesian Beauty Contest, which is, of course, the Monopoly Amendment, which is winning second prize in the beauty contest is not a good thing, and at least not in a Keynesian beauty contest. And then the related literature on sort of probability matching, which when you had a situation where the coin came out 80% of the time this way, 20% of the time that way, you observe people matching probabilities as opposed to picking what they should have done. The correct strategy always to pick the more likely.
Actually, parenthetically, I don't think that holds up. I think that the experiments that I saw, especially in the psychology literature, they were not independent draws. They drew without replacement. And Mo Farina had nailed that a long time ago. When we look at this and they're clearly independent draws, you don't see that.
Yeah,
So I guess I don't believe.
Okay, but let
The
me,
confirmation of that is would be from psychology literature. So they've given up on this.
On probability. But what's the thing that the rational player in this game, with hindsight, should have done? Because what you're picking up when you get the probability distributions matching the probability distributions, isn't it?
No, not really, because look at it, where am I going to spend my next buck? Then I look at the odds on those things, and I look at the price. So I can look at the expected value given the odds that are out there and compare it to my odds. So I'm not matching probabilities at all. In terms of my belief, then the expected values of all these things should be the same, and so the prices should adjust so that my expected value is everywhere the same, and I don't care. That's where I'd be in equilibrium. But, you know,
But
it's,
ought we not to be converging to maybe I'm just being confused about the
Converging average?
Converging to the plurality winner.
well, that might be a model. They don't. That's what I can say. They don't. The plurality winner, if you say the average, we actually compared the average beliefs to the model, and they're doing much better than that. And I think I know why. Because they're learning from the process. But then again, you can look at the equilibrium. I'm forgetting. Yeah.
Run a sequence of these experiments, and then who are the good people? So it's not a homogeneous people that you count the votes. How many people you see so forth. Giving equal weight, but giving more weight and more attention to the experts, the people who have
But they don't know who the other guy is. Well, I mean, I could. Well, if I had more, oh yeah, there's a lot of things we can do. I mean, the businessmen want to do that inside Intel. They want to say, who has best information? You know, maybe we should listen to those. And, you know, I don't know whether that's going to work or not.
it's not necessarily information, it may be skill.
Yeah.
You might be one of them.
Yeah.
Where somebody is.
Then they want to get rid of people, by the way, who have no information. So, okay, that's great. Thank you very much.